the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through a section on determinants or a chapter on determinants. You should be familiar with how to find the determinant of a matrix at this point, of a square matrix specifically, because determinants are not defined for non-square matrices. There's nothing else you really need other than that piece of information, and maybe one extra little theorem that I proved in a previous video. I'll mention that when we get there. And speaking of a previous video, actually I mentioned the following concept in the last video I made, the one that's all about computing a determinant. It was kind of the last few moments of that video. It's a long video, so I would understand completely if you didn't get to that point. Anyway, computing a determinant would be much easier if the matrix we were handed was triangular. And that's mainly because the determinant of a triangular matrix, this is a theorem, so listen up. The determinant of a triangular matrix is the product of its diagonal entries. And just to show you, that's this theorem right here, theorem 2. If A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal of A. And again, if you watched the previous video, we computed the determinant of a 5 by 5 matrix, or it could have been 6 by 6. I can't remember at this point, but it was a beastly computation. And if you can avoid that and just take the product of the main diagonal, that'd be awesome. And we have the skills, by the way, to turn a matrix, at least a square matrix, into a triangular matrix given row reduction techniques. But do row reduction techniques actually affect the determinant? Well, that is what this video is all about. And as a big reveal right at the beginning, the answer is yes. Row reduction operations or row operations do affect the determinant, but we know how they affect the determinant. So here's a group of theorems that I've glued together. These theorems are numbered in the textbook that I use as 3, 5, and 6, but I really think that these theorems should just be glued into a single theorem called properties of determinants. And with such a glorious name, it should probably have a lot more in this list than 5 properties, and there probably will be a lot more than 5 properties by the time we get done with this list. So let A and B be square matrices. I don't need these matrices to actually be invertible to have this conversation. Let's talk about the row operations, and that is actually parts A, B, and C here. If a multiple of one row of A is added to another row to produce a brand new matrix, then the determinant of that new matrix is invariant from the determinant of A. They are basically the same, not just basically, they're exactly the same determinants. So therefore, when you use the row replacement row operation, turns out that doesn't change the determinant. That's pretty awesome. So let's look at part B. What if we have 2 rows in A and we decide to swap them? Which seems like a realistic thing we might want to do, especially if we're trying to get A into a triangular form. We might have to swap some rows. So what does that do to the determinant? Well, if you interchange a couple rows to produce a new matrix, then the determinant of that new matrix is the opposite of the determinant of your old matrix. So that basically means every time you swap rows, a negative appears in front of your determinant. So if you swap rows 5 times, you have -1 to the 5th in front of your determinant. Part C, if one row of A is multiplied by a constant k to produce a brand new matrix B. Now, I'm not telling you the matrix A is being multiplied by k. I'm saying only one row of your matrix A is being multiplied by that k. Well, if that's the case, then the determinant of that brand new matrix is actually just k times the determinant of the original matrix. So those 3 parts to this theorem are really glued to the row operations that we normally perform on matrices. What about parts D and E? Well, those have nothing really to do with row operations, but they kind of make sense. At least D does. D totally makes sense because we know that we can compute the determinant by expanding about any row or column that we want. It turns out the determinant of A transpose should therefore be the same as the determinant of A. Again, because When you take the determinant of a matrix, you can expand about any row or column that you want. So if you say expand about row 3 for A to find its determinant, well, that's the same as expanding about column 3 of A transpose to find the determinant. And finally, this last one right here, the determinant of a product is the product of determinants. That's a very powerful theorem. And then down here, I have the concepts, and I've sort of said these already, but it's worthwhile to repeat. So part A is incredibly powerful as it allows us to perform most of our row operations without affecting the determinant. These are when you're doing row replacements, which I often call the kill step when we're in just a regular algebra class. Another way that you can state A is that the determinant is invariant under row replacements. That means the determinant doesn't change when you do row replacements, when you add row 6 to 7 times row 7 or something like that. Part B, on the other hand, tells us that interchanging rows reverses the sign of the determinant. That's part B up there. So interchanging rows just reverses the sign of the determinant. If you interchange 27 rows, then the sign switches 27 times. Well, you can think of that as -1 to the 27th power, which is negative. Part C, which is that if one row of A is multiplied by K to produce B, then the determinant of that new matrix is just K times the determinant of the original matrix. Well, it's better thought this way, that you can actually factor out a multiple of a row from the determinant. It's not really factoring, honestly, because if you were to factor something out of a matrix, it has to come out of every entry within the matrix. However, a lot of students will think of it as factoring when they factor a 5 out of row 2 or something like that. Part D, which is about the determinant of A transpose being equal to the determinant of A, is very helpful later on. That's when you're performing column operations instead of row operations. That does actually tend to occur, not often, but it does tend to occur, so it can be useful. And then part E, as I mentioned when I said it out loud, is incredibly useful, but we'll have to wait for its usefulness to appear. Now, as I mentioned, I'm not going to actually put down a legitimate proof of any of these because my videos as of late have run very long and I'd like to just power through. Honestly, my voice is getting hoarse. The thing I want to mention here before we move forward is that these first 3 theorems are better written in a different form, at least the theorems B and C, because the reality is you have some given matrix A and you're using row operations to transform that into a matrix B and take the determinant of B. And then you're using that determinant to give you the determinant of A. Well, the way these are written in the textbook that I use, they write the determinant of B in terms of the determinant of A, but the reality is it should be the other way around. So whenever you perform a row replacement, the determinant of A is going to be the same thing as the determinant of the brand new matrix. If you instead do a row interchange, the determinant of A will equal the opposite of the determinant of B. And that's for every single row interchange that you perform to get a brand new matrix B. So if you perform 10 of those, well, you have -1 to the 10th power times the determinant of the new matrix will become the determinant of A. And finally, and this is the one that tends to confuse people, that's why I want to rewrite this, if you multiply a row of A by K to produce B, as this theorem states, the determinant of B is equal to K times the determinant of A. However, it's better written this way. The determinant of A is 1 over K times the determinant of B. So you get this new matrix that possibly you can take the determinant of easily, but you had multiplied a row in that matrix by 5. Well, then the determinant of A will be 1/5 of the determinant of B. And that's a much better way to remember or to, I guess, memorize these determinant theorems. So let's see these in action with this determinant right here. We're going to use row operations instead of straight computing this determinant. Now, just to give you a heads up, this is the determinant that we computed in our last video, and it was a bit of a bear. You can see all the computations there, and you can see that our final answer was -135. So that's our ultimate goal here. You rarely have a determinant that you have to compute where you know ahead of time what the response or what the computed value will be. However, in this case, we do know. And that's just because we did some work previously on this very same determinant. So going back here, again, we're going to keep track of all of our row operations that we perform, and each time that we perform one of them, we'll make a modification to the determinant of A. I'll call this matrix A, and I'll just say the determinant of A is equal to, and then we'll have a list of products that we'll throw on there as we perform row operations. Remember, the only one that doesn't change, or the only row operation that doesn't change a determinant, is row replacement, which is actually the most common row operation, so that's kind of nice. But we're going to start this by swapping rows. So we're going to let A actually equal this matrix. I'll just write it as a matrix rather than leaving it as a determinant. And we're going to perform row operations. So the first row operation, we're going to swap rows 1 and 3. Now, before performing the row operation, I will just make a note that because of that row swap, our determinant of A will be a -1 times whatever determinant we get in the very end once we're done doing all these row operations. A couple notes before I continue forward. The very first note is that you don't want to perform multiple row operations at the same time unless they are row replacements. That's still okay to do multiple row replacements at once, but don't perform a row swap and row replacement simultaneously. It can lead to mistakes. The second note I want to make here is be very, very careful with your arithmetic here, because some things can go wrong. Trust me, I've already done this video once. All right, row replacements. That's what we're going to do right there. And just to let you know, none of those will modify our determinant of A, or in other words, none of those will modify the determinant of what we'll take in the long run. So we don't have to worry about modifying the final determinant with some type of computation. We just get to actually perform these row operations. All right, we get down to there. Not too bad. Now I'm going to take a look at probably the next best row operation here. And you can see if I kept this 5 as a pivot right here, that means I have a lot of fractional arithmetic to kill things off down below. But if I row swap with row 3 and divide row 3 by -3, then I'll have a very nice time with my row replacements in the long run. So I'll start by swapping rows 2 and 3. Once I write that action down, I'll go ahead and go up to this right here and just say, okay, so we have yet another -1 happening. So that is me tracking my row swaps. Let's go ahead and write down the row swap. All right, we performed that row swap, and notice I didn't actually divide that row, this row right here, by a -3 yet, because I don't want to perform 2 of those row operations that will affect the determinant. I don't want to perform 2 of them at once. But I'll go ahead and now divide that second row. Actually, I'll divide it by 3, just to let you know that you don't have to keep 1s in the main diagonal. You can keep them any number you want, but it just makes it easier to have it at least be a 1 or a -1 in this position. So I'll go ahead and divide row 2 by a negative, or by a 3. Now we happen to know from our previous page, if we multiply A by K, so in this case we're multiplying it by 1/3, it'll produce a new matrix B where the determinant of B is 1/3 times the determinant of A. But what does that mean really? It means the determinant of A is 1 over that number, which is 1 over 1/3 or 3 times the determinant of B. This is the much better way to remember it right here. So the determinant of our original matrix is now going to be 3 times the determinant of our final modified matrix. Going back here, I'll just write that here. Remember, it's the reciprocal of 1/3, so I'm going to multiply by 3 here. All right, tracking that, we're good. Let's go ahead and divide that second row by 1/3, or by 3 now. Down to this point, I can now do row replacements to kill off everything below this pivot. Actually, I'll just circle up our pivots, or square up our pivots right now. So remember, row replacements don't touch the determinant. Just be very careful with the arithmetic here. All right, we get to this point right here, And again, I'd like to row swap rows 3 and 4 right now. I know it's an extra little step, but I just prefer to do that, just me personally. You don't actually have to do it. You could take 1/2 or -1/2 row 3 and add it to row 4 if you want to. It actually will not matter if you do that. And in fact, I encourage you to, on your own, try that. It actually will result in the same determinant in the end. So if you choose to go the route that I'm going and you row swap, you have to track a new negative up top. So that'd be -1 to the 3rd. However, if you choose instead to not row swap and you decide, you know what, I'll just kill off this row below by multiplying row 3 by a -1/2 and adding it down below, you could totally do that. You'll get a fraction here, which is not a big deal. All right, now I'm going to go ahead and do a row replacement, which does not affect the determinant, so I don't have to track that. All I have to do is write out the new matrix. All right, and you can actually see our next step is just going to be a nice clean row replacement. And rather than me erasing or writing down a whole entire matrix, I'll go ahead and just do the row replacement right here. I hope you don't mind. So that would make this a 0, and -9 plus 4 gives me a -5. That is our matrix B. And notice our determinant A in the long run is going to be -1 to the 3rd because we had 3 row swaps, times 3 because we divided by 3 at one point in our row operation. So we're multiplying by 3 to get back to our determinant of A, and then times the determinant of B. That'll be a -3 times, well, let's compute the determinant of that triangular matrix. 1 times -1 is a -1, times 1 is still a -1, times 9 is a -9, times a -5 is a +45, and -3 times +45 is a -135, which is exactly what we knew from our previous work the determinant of A should be. So I'm glad that actually worked out. But this really showcases what I'm trying to drive home in this video, which is if you can perform row operations ahead of time, please do. Get it in triangular form because the determinant is much easier to compute when your matrix is in triangular form. You just have to keep track of row operations and what they do to your final determinant. Remember, every row swap causes a negative, and when you multiply a row by k in your row operation process or your row reduction process, you're going to multiply your final determinant by 1/k. Not too bad. Now we're at some extra theorems here. We basically have 2 in a row, neither of which I'm going to prove. I'm just going to state them. We're going to let U be an echelon form of the square matrix A. So you've done some row reduction to get down to the echelon form U. Now, I'm not telling you that A is invertible or anything like that. We just have a square matrix A, and we've arrived at an echelon form. Well, the determinant of A is very much related to the determinant of U, and we've already found that out in our previous example. If you can get A down to a triangular form, which is an echelon form, then we know the determinant of A is basically a slightly modified version of the determinant of your echelon form. There are some negatives possibly involved, and you still have to multiply all of the diagonal elements. And that's exactly what this is saying. The determinant of A is -1 to a power, we'll talk about that in a moment, times the product of all the pivots in U. If you look at our previous example, notice I've squared up or circled, all of the pivots. And if you want the determinant of this specific matrix B here, which is an echelon form, you would just go ahead and take the product of those pivots. If it turns out that one of those pivots, let's just pretend, was not a pivot, in other words, let's pretend as though that was a 0 down in that bottom right-hand corner, I would still say, take the product of the diagonal elements. It's still going to be the determinant of this matrix. We have a theorem for that from our previous work. But this theorem's just kind of stating that again. So if A is invertible, then A can be row reduced down to the identity matrix. In other words, there's a pivot in every column, and therefore the determinant of A is going to be -1 to a specific power times the product of all those pivots. Great. But what if A is not invertible? Well then, one of those pivots has to be 0. We've actually proven that in a previous video. And therefore, if one of those pivots is 0, you have a bunch of numbers times 0, and so the determinant of A will be 0 when A is not invertible. Again, I just want to remind you that we have this in our list of equivalent statements for the invertible matrix theorem. We actually proved it in a video not too long ago. I called it D16 for determinant topics. If the determinant is not 0, then A is invertible. If A is not invertible, then the determinant of A is 0. And we proved that, so I don't have to actually make a big stink about it. One last little note here, that power on -1, that R right there, is just the number of row exchanges in the row reduction process of A to U. So we've been talking about that, so that shouldn't be new. So this theorem almost seems like an excessively repetitive theorem. There's really no reason to introduce it because we already know this is true from our previous work. So if I was writing down a list of critical theorems that we have learned up to this point, I'd probably not include this because it's already a result of something that we've already talked about, so it has already been written down in a previous theorem. Likewise, we actually wrote this down too, and I just showed you it. A square matrix is invertible, in other words, A is invertible, if and only if its determinant is not 0. Again, I already had that written. So it turns out that these two theorems that I listed in a row are actually just repetitive theorems, but if you're learning out of the textbook that I use, the author repeats these with their own separate theorems, but in reality, we've already introduced ourselves to these theorems. So finally, we get down to this bad boy right here, and it says use row operations to compute the determinant. Well, I'm assuming that this determinant is going to be 0, just because I have written it after those past two theorems, and we've already computed the determinant of a matrix. But let's just go ahead and play the reindeer game and pretend as though we don't know that. Let's call this matrix A. And let's do some row operations. Remember, I'll write over here the determinant of A, and it's equal to some moves times the determinant of our resultant echelon form. Notice I'm calling that U, just because I'm going to get this down into an echelon form, and we have been using U to stand in for upper triangular matrix or for echelon form. All right, first thing I'm going to do is row swap. And once I write that down, I'll throw down a -1 to the first power right here. Going back, let's perform the row swap. And now let's use row replacements to kill off the 2 and the -3 right there. Remember, these do not change the determinant, so these are freebie operations. Now, technically at this point, I can actually just stop. The reason why I'm saying that is because notice row 2 and row 3 are the same rows. That is, if I add those two rows up, they're not exactly the same, they're actually opposites, but if I add those two rows up, I will have a row full of zeros, which means I will have a row without a pivot. So that means in my next step, I would have just added those two rows together to get 0, 0, 0, 0 as our new row 3. And that means we have a row without a pivot. And according to the invertible matrix theorem, a row without a pivot, so if A does have a pivot in every row, then it is invertible. However, if there is a row without a pivot, A is not invertible. And since A is not invertible, that immediately implies the determinant of A is actually equal to 0. I didn't have to finish this entire process. I just had to get it to a point where I found a row of zeros. Once I find linearly dependent rows, I know that I have a row without a pivot, which tells me A is not invertible, which means the determinant of A is equal to 0, and we're done. Notice how keeping my eye out for something like that can speed up the process. So I challenge you to look through as you're doing your homework problems and just pay attention to little things like that, where if you have two rows that can be multiples of one another, then you immediately know the determinant has to be 0, because two rows being multiples of each other means that you can kill one row completely off and make it all zeros, which means you have a row without pivots in your final matrix, which means even if you could write that matrix as an upper triangular matrix, one of the diagonal elements is going to be 0, so the product of a bunch of numbers with 0 is going to be 0, so your determinant is 0. By the way, at this point in a linear algebra course, actually at many points up to this point and thereafter, students will say, wait, hold on, how many ways can I actually showcase this is true? Because you just said if you get it in triangular form, you'll have a 0 in one of the diagonal elements, and the product of a bunch of numbers with 0 is going to be 0, therefore the determinant is 0. However, when you did this problem, you basically said, oh look, I have two rows that will mangle each other and one row will become 0, so I don't have a pivot in a row, so therefore A is not invertible, so therefore the determinant is 0. The fact is, there are many ways to get to this very same answer, that the determinant of your matrix is 0. So don't just think that what I'm saying is the law. There are many other ways to do this. You should challenge yourself. Try different ways to showcase that the determinant of a given matrix is 0. Anyhow, we're done with this video. We're done with this material in this section. So I hope you have a wonderful day. Be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine, just